நான் மேடம் கூட ஒர்க் பண்றேன், சுரேஷ் பாபு. சரி, நான் இங்க பேசிக்கிறேன், கால் பண்ணிக்கிறேன். ஓகே, சரிங்க. ஓகே, தேங்க்யூ சார். சரிங்க, பார்த்து.
Good morning, ma'am. Uma, ma'am. Good morning.
Good morning, sir.
Ma'am, shall we start the session now?
Yes, sir. Sure. Yes, we can start.
Good morning, participants. Before going into session, so I will give small intro about our today's expert. Mrs.Umamaheswari, working as a chief consultant in Bharat Electro Corporation Limited, Coimbatore. Is pursuing his PhD in the area of EMI filter design, ME in completed his ME in embedded system and BE in electrical electronics engineering in Amrita Institute of Technology, Coimbatore. Her area of expertise: high speed PCB design, post processing of PCB design, package system design, EMI and SI analysis, power electronics, cross functional analysis. She published more than 10 technical articles in referred national and international journals and published books. The title of Power Electronics with MATLAB, Cambridge University Press, London, Simulation Tools for Electrical System, Elsevier Press, UK, Electrical Machines with MATLAB in Press Nova. Conducted 1 credit courses for UG and PG students in the area of PCB designing system and EMI mitigation methods. She is certified JLPTN3 Japan language proficiency test certificate holder. Conducted courses for students and industry persons for Japanese language and also Japanese language translator for technical documents. So, and also she acted as a keynote speaker in various international and national workshops. I welcome you, ma'am. Now session is yours.
Thank you, sir, for inviting me for this session. So, can you share the presentation, sir?
Yes, ma'am. Yes, ma'am. I will share now.
Okay.
Yes, ma'am.
Okay. Yeah, today, so my topic of presentation is EMI penetration to smart grid. That is electromagnetic interference related to smart grid and other related applications in and around that smart grid. So today's agenda is, next slide, please. So today, topic of discussion will be what is electromagnetic interference compatibility in and around smart grid, and we'll see the sources of electromagnetic interference in the smart grid and recent advancement devices related to power electronic devices. Finally, electromagnetic measurement, that is every product has to be measured and tested and has to obtain the certification part, so that and how to measure and how to simulate. So we'll touch upon that topic in the final stage. So initially we are going to see about the introduction part. So what is smart grid actually? So next slide. So what is smart grid? Smart grid, as we all know, it is an electricity network which enables two-way communication. That is, one is electricity and the data, other thing is data. So next slide, please. Data with digital communication technology. So here we are enabling to detect, react, proact the changes happening inside that thing. So all the smart grid should have a self-healing capability. So various technologies we can involve in this smart grid can be renewable sources like wind, other electric cars, and transmission systems, etc. And according to IEC, that is International Technical Commission, so it defines the smart grid as a concept of modernizing the electric grid. So smart grid is integrating the electrical and information technology between the point of generation and the point of consumption. So with this introduction, we'll get into the next slide. So here, the picture shows the interoperability of the devices. So here in the interoperability means the basic ability of different computerized products such as or systems to readily connect and exchange the information between each other. So you can see various components are connected together. So just click on the slides. Yeah, so the various each entities has the communication and the IT information and the power information. So all these are connected together to have the interoperability between the smart grid interoperability. Next slide. So altogether it is called smart grid system interoperability. Okay. So coming to the grid modernization, so what it should have the basic characteristics such as healing, self-healing, active participations by consumers in demand response, operate resiliently against the physical and cyber attacks, that is coming back to the original position in the case of any issues. High power quality, accommodates all generation and storage options, enables a new applications, operates efficiently. So these are all the major characteristics of this grid side. The principal, so various technologies, various department or engineering disciplines involved in the smart grid are power and energy distribution, radio frequency communication, information technology, cyber security, electromagnetic compatibility, and spectrum management. So here, each and individual, every department is very important to have the its own it has to perform its own work. So similarly, the electromagnetic compatibility is very keen, which affects the various things which will be seen in the later slides. So the principal main thing is if any error comes, that is if any damage or anything happens, it should isolate the affected areas and it should redirect the power flow or data flow to some other proper channel. So it is the main characteristic, the main principle behind this smart grid. Next slide. So this system, power system, generally has all other network integrated together, but along with that, we are having the high speed data communication, like whatever the digital data has to be communicated either Wi-Fi mode or wired or wireless mode, it has to be communicated. So next. Here all the communication information infrastructures are connected together to form this integrated disciplines. So that is what this slide represents. So next. So common standards has to be followed. So IEEE 2030 is a smart grid development guidelines available in that standard. So it covers the cyber security, network communication, electric transportation, electric storage, advanced metering infrastructure. So everything, it has its own standard which has to be followed for implementing the smart grid facility. Next. Again, the smart in the smart grid area, it is EMC is an important factor where we need to protect the devices either from the emission side, or it has to be immune in the presence of electromagnetic interference. So for that, we have to test the devices in the IEEE or any other standards available related to the thing. So standards and all we will be seeing in the later slides. Next. So, what is electromagnetic interference? So, electromagnetic interference means so we have the many digital devices around us. So, unintended electromagnetic emission will be happening due to the high speed operation of the frequency operation of the circuits. So, we will be having some impact of this electromagnetic interference. Due to that, we need to test the system based on the emission or the radiation level. So the events can be the emission or conduction, radiation. So various events are present in the thing. So which will be it has to be keenly noted by the any designer or electrical engineer or electronics engineer. So whatever it may be. And electromagnetic susceptibility is how well the system performs in the presence of electromagnetic interference. So that means that immunity purpose. So altogether forms the electromagnetic compatibility. Next slide. Because of this EMI issues, we will be having the malfunction, degradation of the performance of the system, or performance effect due to this issue with the proximity system. So all these are the main causes of the EMI. So there are various types of electromagnetic interference that is based on the source. We can split into natural or man-made. That is unintentional or intentional, and based on the period of interference, it can have continuous interference, impulse noise, as the name itself we'll be getting to know, and based on the bandwidth, it will be having the narrow bandwidth and broad bandwidth. Next slide. And commonly we can say the various environment, that is information technology equipment, will be having CISPA 24 or IEC standards. Will be we need to follow these standards. And substation equipments IEC 60-255-26. So this standard has to be followed. For wireless devices we are using in the thing, we need to follow the IEEE standards. And so for all this, the basic thing is emission and immunity level has to be maintained according to the standard set level. So as I discussed, the main events of this electromagnetic interference event are source, path, and victim. The source and victim are coupled, either conductive medium or the radiative medium. So that can be conductive in the sense it can be a capacitive or inductive effects, and radiative means it can be in the dielectric mode or in the means of air or whatever dielectric thing. So source and victims are the major side to be noted in this electromagnetic interference. And based on the source levels, that is that can be a receiver or a transmitter or whatever it may be, that has to be keenly noted that the source we need to mitigate the electromagnetic emission at the source side, and the conduction path or radiation path, we have to either spreading the spectrum, or we have to mitigate this transmission line propagation. So next slide. So next slide, please. So this is what we discussed. Radiated interference, it is a means of air or electromagnetic in the case of PCB, it can be a dielectric or air, we can say, that is escapes from the source and spreads out in the space according to the law of wave propagation. So that is the radiated interference. And in this electromagnetic environment side, we have to cleanly note the 4 points, that is RE, CE, CS, and RS. So RE is radiated emission, CE is conducted emission, that is from the emitter side. And the susceptor side, we need to see whether the system, that is receivers, analog circuits, or digital circuits, are including human beings, we have to, those susceptor or victim side, it has to be immune enough to withstand the electromagnetic effects. So that is called conductor susceptibility, radiator susceptibility. So these four parameters are very, very keenly noted in the case of testing or measurement. So these are all definitely undergone the EMI regulation. Next slide. So the possible threats can be in the smart grid areas, power transients, radio frequency interference, electrostatic discharge, power line. So next slide. So power transients here means the momentary burst of energy induced upon the power or data or communication lines, whatever it may be. So this can cause the damage or upset or total malfunction of the system. And next is the radio frequency immunity. So next threat is an radio frequency immunity. So this can be a radio transmitters, the onboard electronic systems which may be exposed to very high radio frequency electromagnetic fields. So like voltage regulators can also be affected with this help of radio frequency emission. So the frequency level may be little high compared to the digital communication. So this has to be mitigated. It is also a threat. So with the help of a two-layer PCB being the one layer ground layer in the any converter or whatever the design you design. So this helps a lot to get the system immune with the help against the radio frequency. Next is the electrostatic discharge. We can say there is a potential difference between the object and the ground. It depends on the humidity and the property of the material, as we all know that, and the temperature also. So we know the human are very ready source of ESD. So we have, if you see the next slide, the graph plots. Next slide, please. So that is a curve for the ESD curve for the human body. So you can see the very high rise time that is current with the particular with the minimum duration. So this is also a very major threat in the case of the any electronic components, or you can even you can say in the smart grid applications also. Next. So because of this ESD, we can experience two kinds of failures, like catastrophic failure, latent defects. So catastrophic failure means it causes the permanent defect in the system. So you can see in the image, the junction of the copper connection is melts because of this ESD level. So if it is in the top layer, we will be identifying with the vision itself. So if it is in the middle layer or something, we cannot know where the defect has happened. So this is a complete malfunction, a complete failure of the system. So latent defect means it can occur when an ESD sensitive item is exposed to an ESD event. So it may continue to perform the intended function, but later on it may transfer to the catastrophic failure. So so this is the this affects the mainly performance degradation. So maybe the communication delay or wrong communication. So it can happen because of this delay. So ESD is a very, very major threat among all this. Next. And the fourth threat is power line fields. So power lines and transformers, we can say this is not a problem for the microcontroller based applications, as power line because frequency is very low, so it will not be get affected the thing. And but in the power line field requirements are usually imposed on electronic system to make sure there is no upset because of this threat. And apart from these four threats, we have other next slide. Next slide, please. We have the wireless transmitter threat, and this can be simulated with the help of the frequency range, power levels, modulation, and the criteria of acceptance. So these power ranges from 5 watts to 1500 watts. So these are all wireless because of the wireless transmitter electromagnetic interference. So next is the coexistence of the please. Coexistence of the wireless devices. This is also one of the major threat we can see. The coexistence here refers to the function of different wireless devices and standards in the same frequency band and same coverage area and the same time. So this we can say is a coexistence of the wireless devices. So wireless devices can cause and receive interference. So this also the major thing has to be noted finally. Next. So here we can see the standards like electromagnetic interference standards. IEC and EU are define the standards for various things like harmonics, voltage fluctuations, power frequency variation. So for various individual topics or threads, it has defined the standards. So it has to be addressed. And for meeting the standards, we will be having a good voltage quality and power quality as well as a current quality. Next. Some of the field experiences we will see here, like a kilowatt meter in households sending data signals on the power line have caused interference. There are also cases reported where electrical apparatus like household appliances have interfered with the electronic kilowatt hour meters with some performance degradation. Like it has sent the wrong data in the to the grid, or it's getting the grid from the wrong informations. Like it'll, for example, if the generation will be one particular value, so it will send the wrong data to the grid, and will have some other malfunction like miscalculation or whatever it may be happen because of this. And the third one is emitted disturbances interference with the transfer of kilowatt meter reading, kilowatt meter reading as signal on power lines. And like any other power electronic based photovoltaic, solar or wind energy equipment may emit disturbances causing the voltage fluctuation on unbalance. So these are all some of the field experiences which are noted in the industry. So this is the EMI issues related to the power grid side. So we can see end user side, various end user or grid operations. So various things are listed here with the possible example scenarios. So this we can go through later. And EMC directive on electrical network has defined the motto here. So for example, so this paragraph is the electromagnetic EMC directive statement. Like this, what does this mean is that both parties are responsible for networks being equipments as well as for the equipment connected to the network are supposed to contribute the EMC. So this is what they are trying to say. Next slide. So the main point we have to take away is the objective of the protection requirements for equipment, including fixed installations such as electrical networks and connected equipment, is for achieving the EMC. So we need to achieve this EMC at a design stage or at a prototyping stage. Next slide. So we'll briefly see the sources of the electromagnetic interference in smart grid. So main sources are the power electronic interfaces, that is PEI, power line communication technology PLC, flexible AC transmission system, and other communication technologies involved in the smart grid system. So we'll see the smart grid first EMI issues in the power electronic interface. Like so, it has the electronic areas in this interface means here is power converters and smart meter. So power converters have the power switches or power electronic switches, we can say. So because of this switching capability, there are main return path, that is return current, that is di by dt, dv by dt value, we can see. So that has increased because of this switching nature in the electromagnetic interface power circuit side. So that has to be mitigated in the thing. So this is the major issue which we see in the smart grid area. Next slide. So here, so power converters we see here, AC, DC, AC, AC. So various converters are available. So major components are rectifiers and inverters are the main source for this electromagnetic interference. And we need to mitigate those di by dt and dv by dt value by various methodologies we followed, which will be the next slide, which will be discussed in the next slide. So there are major issues because of these converters, EMI, losses, and harmonics. So these three are major issues which are interconnected or interrelated with high efficiency, quality, or cost, or size, whatever it may be. You can skip next 2 slides. These are all basic information. So power, next slide. Yeah, power switches here. Power switches also a major source of electromagnetic interference. So switches, normally ideal switch means it can handle unlimited current and blocks the unlimited voltage. So this is in the ideal scenario. And voltage drop across the switch and leakage current through the switch will be zero in the ideal scenario. But in the case of practical scenario, it is not possible. So there will be some amount of di by dt, this is leakage current and the leakage voltage. Voltage drop will be there in across the switch terminals. So that because of this rise time and fall time, etc., of the power switch. And this leads to the losses. Yeah, next. This leads to the losses, harmonics, and EMI. So switching frequency and dV by dt we can control based on this. It is a trade-off actually. So we need to have the higher switching frequency, and in the case of higher switching frequency, we'll be experiencing the higher dV by dt and di by dt. So it will be if you increase the dV by dt and dV by di by dt value, it will automatically increase the EMI value. So based on the set level of the standard which is to be followed, like per IEC or standard. So that has to be decided by the electromagnetic engineer or designer, and we can have to play around this rise time and fall time. So next slide. Again, this is the power converter side. Next, power converter in the smart grid area. This is also one of the other source. So this is some of the mitigation techniques like field programmable logic array technique and random pulse width modulation technique, and some other like filters, introducing the filters in the input and output side. So these are all the typical methods to be followed to reduce the electromagnetic interference in the design stage of the power converter side. The second, this is in the interface side, this is smart meter. The smart meter has the integrated, many integrated circuits, microcontroller unit, metering chips, voltage converter, current converter, peripherals circuits. So various components are available in the smart meter side. So this facilitates, the smart meter facilitates the real-time energy consumption and billing, voltage and frequency data measurement, loads, connections and disconnections, and diagnostic information communication, and efficient energy usage. So these are all the main uses of the smart meter. Next, and some communication technologies we use in the smart meter is radio frequency, wireless communication, and power line communication. So these are the EMI effects may be data transmission error and data corruption error, and compromise energy reading affects the effects of the field on the other circuit elements. So these are all some of the effects we can see. So by simply coating some of the material with some material like iron powder on the surface of this unit, we can reduce this particular radio frequency interference in the real field, in the industrial field. Next. So second source of the smart grid EMI source is power line communications. Like power line communication here means the electric power transmission for data, electric power and data transmission. So these benefits can be the obviously the cost benefits, cost savings will be there, and narrow band PLC and broadband PLC can be used power line in the power line communication. So power can be in the very low level frequency range, and the data communication may be the high frequency communication. So these two has to be addressed in the to mitigate this electromagnetic noise. Next. So based on the distance of the communication, we can choose either wireless or wired communication technology. So these are all the typical spec it is given for the communication technologies used in smart grid. And some of the mitigation techniques of this source of power line communication is we can use a cognitive EMC technique, or injection of 180-degree phase out of phase auxiliary signal to nullify this noise, and some passive techniques like capacitors, capacitive couplers, and etc. to spreading the noise. Or these are all some methods to use for the mitigating this electromagnetic interference. Next source is fax devices. So this is the flexible AC transmission system used for AC transmission system performance and efficiency enhancement. So what does it has? This smart meters, power electronic based devices, or the smart meters, small size and cheaper fax devices connectors we are using, and the operation of fax switches leads to the electromagnetic any switches leads to the electromagnetic interference noise. So that is what we discussed. So the fact controllers or fact devices, fax, are based on the controlled switching power electronic devices used for power conversion consumption compensation. And some of the equipments, that is general fact equipment based AMI depends on the following categories. Like electromagnetic interference can be mitigated with a very basic thing like layout parameters itself. We can control the thing, and having the very good thyristor value switching characteristics, and stray parameters associated with the thyristor controlled rectifier, thyristor switch capacitor, static synchronous compensator, passive filter or active filter, or neural network, which helps the some of the mitigation techniques used for a fax system. And fourth source is other communication involved in smart design, smart grid, that is wired technique or wireless technique. Wired in the sense, for example, home area network, business area network, neighborhood area network. So these are all the some of the communication infrastructures which can be adopted based on this designer's perspective or the application perspective. In wireless communications are GSM, GPRS, 3G or ZigBee, whatever it may be. And IEC 61850 based WLAN enhances the protection of distribution substations through the intelligent monitoring and control using sensors and intelligent controllers with wireless interface. So similarly for various technologies, various communication, wireless communication or wired communication technologies, each has its own standard. Next. Next slide. And other in the same other fourth source of this smart grid is other communication side technologies. We have other things like IEMI and HEMP, other things. So IEMI can be mitigated by separating the electronic equipment from interference sources, ensuring the equipment is properly shielded. And HEMP is actually a generated due to the high altitude nuclear burst. This is and the next is the electromagnetic storm. It is a natural electromagnetic storm. This kind of storm, people say it occurs in the once in a century. So next slide. So in the next slide, this represents the storm of electromagnetic storm happen in the high altitude level, which can be experienced in the very longer area. It is larger area. So in the US side. So this is another thing. Then it can happen in natural electromagnetic interference. So next. The main thing we need to remember is smart grid is no doubt the future of the power system, with its flexibility, reliability, efficiency, and smartness being inexplicable possibilities to the power grid. So we have to clearly identify the source of the electromagnetic interference and mitigate this thing. So this in and around the smart grid area. So that is the point we have to remember. Next. So next is the recent advancement devices used in the power electronic industries like WBG devices. Next slide. We have reached the maximum level of the materials capability. So alternatively, we have to go high efficiency and high power density devices like WBG devices alternate for this thing. So WBG devices are wide bandgap devices which have high temperature withstanding capability as well as the high switching frequency. Next is, we'll go through this quickly, this particular topic, and this slide shows the comparison between this SI and WBG devices, this SAC and GAN devices. So you can see because of the switching and other unique characteristics of WBG devices, people are using WBG devices nowadays, and we have to clearly note that this, because of this high frequency switching characteristics, there will be definitely the electromagnetic interference effect because of this EI by dt and dB by dt value. So we have to mitigate that in the design source, design layout itself. Next slide. So this graph shows the comparison between the characteristic of this SI and versus the WBG devices. So you can see the radiated emission that is in the marked the rated EMI side. You can see the minus 40 dB level of conducted emission is achieved here, and we can see the CISPR standard says that this particular level, and so we have to clearly measure those conducted emission as well as the radiated emission, and we have benchmark with the particular standard, whether it is a smart grid or the EV or any other application. We have to select the particular standard and have to benchmark these values. Next. So the outcome is in the previous slide is increase the spectrum of the noise EMI noise source, and EMI noise is generated by the WBG devices will be higher than the SI devices. So these are all the outcome which can be arrived from those graph. Next slide. So you can see the characteristics comparison between the system with SI and WBG devices. So based on the frequency, so we can select, designer is capable of selecting those particular device, WBG or the SI devices based on the need and application. So these are all the some of the points listed here. Next one. So other factors that are involving this electromagnetic interference is impedance imbalance in the path, electromagnetic propagation path or transmission path. So this causes the common mode EMI noise current to flow to the ground through the parasitic capacitance. So the return path will be, it will not be a lengthy path, or it will not follow the proper return path. So because of that, there will be a leakage current. And the impedance of the parasitic capacitance is inversely proportional to the frequency. And with the high switching frequencies, the noise of WBG devices will propagate through path and reduce the impedance. So that is the major thing. Next slide. These are all the techniques given here to increase the reliability of the power converters. For example, to control the radiated emission, just introducing the ground inductor. So similarly, various techniques are available to increase the reliability of this power converters in the smart grid applications. So these various techniques are available. So based on the domain or based on the area, it has to be selected by the designer. Next. So these are all some of the major research topics are open for the researchers. So this table is taken from the IEEE thing. So if you are interested in this electromagnetic interference research area, it can be followed. So there are various research topics are yet to be done in those areas. Next. So as a summary for the WBG devices, it has a very good performance. At the same time, we have the electromagnetic interference issues because of this high frequency and other advantages of this WBG devices. It has to be mitigated in the design stage itself, and it has to be measured once the product is manufactured, once the component or the system is manufactured. So next is the EMI design strategies which can be followed in the design stage itself. So transient protection on all modules has to be performed, and high frequency filtering cable has to be implemented, and careful circuit layout by the PCB designer has to be done. Cable and module shielding has to be done. Local filtering and decoupling can even plays a major role, and local shielding on the most critical circuits also has to be done. So these are some of the EMI design strategies. Next. And after designing the design circuit layout, it has to be simulated by the particular simulation tool. Like there are various simulators are available. That is EM simulator, circuit simulator, behavioral simulator. So EM simulator, which solves the equation, that is, which solves the problems using the Maxwell's equations. That is electromagnetic simulator, and there are various domains like time domain and frequency domain are available. So based on the designer or application, we can select the time, either time domain or frequency domain, and various methodologies are available like FIM, MOM, like, so that has to be selected, and we have to run the simulation of the circuit. And the same circuit can be simulated using the circuit simulator in the prior to the EM simulator level. And this solves this particular simulator solves the equation with the help of Kirchhoff's voltage law, current law, with those relationship. So a designer has to simulate the circuit using the circuit simulator, and afterwards it has to be simulated with the help of EM simulator. And the third one is the behavioral simulator, which solves the model, which is used in the model-based simulation, and tables and transmission lines and other passive elements. Uh, uh, so this abstract level simulation. So a combination of these three will do for the entire system or component simulation. Next. So these are all the EM simulator tools available in the market. So I use EM Pro for my research work related to the thing. So my research work is in the area of high speed PCB application, electromagnetic interference mitigation techniques. So I use EMI simulation, EM simulator for EM Pro, which is the Keysight product, and along with the ADS tool, which is a circuit simulator. It is inbuilt with the particular product, and which will be very useful and user friendly tool too. Next. And other apart from the design level, we can have the hardware solution as well, which is fabric over foam and shielding, electrically conductive filter like common mode filter and differential mode filter, ferrite beadings, introducing of the ferrite beading, grounding, bonding, spatial placement of hardware so that the spreading the spectrum of the noise level. So these are all the various hardware techniques used for the mitigation part, apart from this design strategies. Next. And so various level in the design side, we have to identify the PCB level, module level, and software level. Suppose if you're using the smart meter with the data communication technology, so there will be major ICs or other FPGAs will be sitting there. So and the software embedded code, if you are using that, has to be software also. The code also plays a major role in the case of electromagnetic noise introduction. So coming to the PCB level, next. So this is IC level side. IC level, what is the rule of thumb is suppress at the source or harden at the victim. So this is the rule of thumb normally to be followed, and turn off or on the high speed lines when it is not needed. So that is the inside the component level, and care should be taken for clock drivers. So that is the switching that will create a switching noise. Next. In the PCB level, you can identify the most critical circuits like clock signals or memory signals. Also, whatever the most high speed frequency carrying signal, it has to be identified, and we need to plan the board layout properly so that the impedance mismatch should not be there. Select an appropriate board layout and isolation with care, decoupling the power, bulletproof the interface, and considering multi-layer board also. It's one of the design technique at the PCB level. And next. So this is what we discussed earlier in the PCB side. Next slide. Identifying the most critical circuits, reset signals, interrupt signals, and control signals, like etc. And small capacitors and ferrite beads or resistors are very effective as filters against the spikes and transients. So these are all the PCB level identification of the most critical circuit. Coming to the next. Coming to the layout side, we need to have the group of circuits by the speed of operations. So we need to group the circuits, like digital and analog has to be separated. Otherwise it will create a noise. Likewise, based on the speed of operation, it has to be separated. Next slide. So this has to be a proper board layout. The top side represents the proper unnecessary layer. There is bad layout, we can say, where all the circuits are combined together. But the good layout we have, this is the planning of the layout. So we need to place the digital and analog components are mixed. In the case of mixed board design, it has to be separated based on the speed of operation of the signal. Next. And selecting the appropriate board layout, the third one is the impedance of the level has to be balanced. So that is continuous and broken of the return path will be the major trend. So it should be continuous path. If it is broken in the high speed signal, it will be create a leakage current to thing. So we have to minimize the other the crosstalk also, it has to be minimized in the PCB level. Next. So we can say you can see the crosstalk is in between those two lines or three lines are there. So this is a cross section of the PCB. So the two between two traces, that is two wires, you can say the crosstalks of the signals are merged together. That is that is actually we can say it's a crosstalk effect. So it has to be separated with the help of distance, with the help of lengthy placement. So then we will avoid the crosstalk effect. So this will happen only in the high speed operations. Next. So this is the typical 6-layer board cross section shown here. So based on the speed of the thing, if it is not if it cannot be accommodated in the same layer, it can be shifted to the other layer. That is the purpose of this multi-layer board. Next. And the fourth technique is isolation with care inside the PCB. So we need to have the isolation here means the return path of the driver receiver signal. So normally the signal or power interfaces between the isolated area has to be taken care with the help of a EDA tools or other calculations methods which is available in the this particular area. And isolations with the ferrite or inductors or common mode chokes or can be used in this purpose. Next. So you can see in the case of low frequency operations, from the driver to the receiver, it takes the least resistance path. So the driver and receiver circuit has a signal trace routed in the top layer, and the green layer represents the ground plane, and the ground plane, the return path directly it goes to the lead uses the least resistance path from the receiver to the driver. But in the case of high frequency, next slide, it will not take the least resistance path, it will take the least inductance path. So that is a major difference between the high frequency and low frequency PCB design area. So if the ground plane is a continuous plane, there will not be any problem in the return current. If it is a broken path or we are not placing the enough ground copper in the beneath layer of this driver receiver circuit, there will be a leakage current. It will not follow the particular return path, correct return path, and it will follow the its own path, and it will create the common mode noise, and it leads to the electromagnetic interference. So this is the root cause of this particular noise. Next. So as we see in the previous slides, so the low frequency side, the component will react one kind, and at the time of higher frequency applications, the same component will react with some parasitic effects. So that is the equivalent circuit it is given here. So we need to design considering those particular parasitic effects into the component level. Next slide. So decoupling power, as we know, every IC has to be decoupled with the help of small capacitors like 0.01 microfarad and 0.1 microfarad. This in the case of high frequency operations. This high frequency operations here, where it applies is the data communication in the smart grid. So you can correlate that in a very well. And this 0.01 microfarad will immediately supply the power demand of the IC when the device is switched on. So that is the purpose of decoupling capacitor in the data signal communication side. Next. And cable side, we can clearly use the fiber optic cables, which can reduce the this no particular noise, but we have to play around the cost and other factors too. So the interconnection of the devices has to be clearly measured and identified by the product designer. So next. And the general term is bulletproof the interface. So whatever the interface you see, it has to be we need to bulletproof it, like filtering and the power interfaces, like we have the power interface or signal interface. So these has to be protected by with the help of few high frequency capacitors or the shunt capacitor. So like power or signal based on the interfaces, we can have the bulletproof. Next. And at the module level, mitigation is first seal all the seams. So that is also one of the rule of thumb to be followed. And second, filter all the penetrations. So this is the major thing which has to be in the module level. And the thin conductive coating will help on the module. It will be a great effect in the noise mitigation. Like nickel paint on plastic, which reduces a 60 dB of protection, and vacuum plating on electroless deposition on plastic, which gives the 80 dB of protection. A steel or aluminum box can protect the 120 dB of protection. So these are all the simple techniques apart from the module level, apart from the design level. And as I discussed, the software level, a few lines of code will work wonders. Like watchdog timer can prevent the becoming the lost in an endless software loop. So this is often a separate device, although many microcontrollers incorporate the internal watchdog timers. So this is a simple example of the software code. Next. And EMC precautions in the design stage, what the designer has to do, designer has to have clearly the hot conductor area, equipotential conductor, and external cable analysis. So these things has to be done in the converter topology side, and the cabling control side has to be done, and the risk of oscillations and immunity testing. Finally, the immunity testing has to be done. That is characteristic testings we can see. Input filter. The purpose of the input filter is to reduce the interference, and all the noises can be filtered by the internal filter, and suppress the emission at the source level, make the coupling path is as inactive path, and make the receiver and less vulnerable to the emission. So these are all the need of EMI input filter. So next, the major part is the measurement and testing side. Coming to the measurement side, so these are all various standards available like CISPR. So each and every zone or region has its own standard. Like European Union, that is follows European countries follows the European Union standards, that is EU and CISPR. And IEC worldwide is we are following the IEC standards, like IEEE and other normal standards are available. Various standards are available. For example, if you want to check for the ESD immunity, we have to follow IEC 61004-2. Likewise, for everything we have the standard number, and against that standard it has to be checked for the devices. Next, there are 3 kinds of standards in the worldwide. The organization defines the 3 standards, like generic standards, basic standards, and product standards. So basic standards generally represents the general considerations, definitions, terms, rules, guidelines for emissions and immunity testing. in the test method. So this is a general kind of thing which has the basic standard. So generic standard has the limits and maximum test levels for the products in a particular EMC environment for which there is no product standards exist. So product standard has its own limit and maximum level for the particular area of application. For example, EVs, smart grid, like so any particular application, there will be a particular product standards will be available. If there are no product standards, we will have to follow for the generic standard. So these are all the 3 standards which has to be followed to make the compliance ready product. Next. So this I have listed for the EMC standards related to the smart grid. So these are all the many standards, and each and every stage it has to be followed, either community, either CE or first in the very beginning we saw the 4 main parameters like conductor emission, radiated emission, conductor susceptibility, radiated susceptibility. So for ESD, so these are all the 5 parameters which has to be clearly noted against these particular standards. Next. Again, this is so previous 2 slides were standards, and each and every country has its own regulation type. So we need to initially first follow the standards using the particular standard number, and how we measure against the thing. We have to send our product to the EMC lab or EMC lab, and we have to specify the particular standard number, and against that number it has to be measured. So once the measurement is done, that particular report, the test report, has to be sent to these regulatory bodies like CE, FCC. Based on the country, we have to specify particular regulations. Then only the product can be taken to the market per particular region. So otherwise, it will not be. They will not accept. That country will not accept this without this regulation. So this is called a certification process. Next slide. So this is the market regulations commercial for commercial products I have shown here. You can see each and every country has its own regulation certification. Next. So importance of EMC testing. This is actually for radiated emission, and for reliability, to prevent the rework, potential hazard, to avoid the potential hazardness, to meet the regularity requirements, to improve the product performance, to reduce the risk of costly non-compliances, and to reduce to strengthen your competition position in the market. That is very important. And to safeguard sensitive analog and RF circuitries, calculating ESD level. So these are all the major terms, major points for this particular EMC testing for radiated emission. So here testing means it is hardware testing. So previously, using the EM tools, we can measure conducted emissions as well as the radiated emissions using the 3D modeling or other technologies available in the particular EM simulator tool. Whatever you can choose, it is possible to simulate the emission and the radiation levels. Similarly, we have to measure the particular product into the EMC laboratory for actual testing. So we have to compare. So if simulation results has some deviations in the noise level, we can improve using the design layout and re-simulate the structure. So that way in that way the EM simulator tools helps us to redo the design. Once the design is the simulation results are fine to be okay, and we can go for the EMC testing after manufacturing. So next slide. So this test types are infrastructure test and inter-system EMC tests are available in the laboratories. So that is intra-system is for stable operations and performance and quality. Inter-system is for protection and the radio protection of radio service or using which undergone the radio law. That is, we can say that is a regulation and a certification process. So these has to be followed in the EMC laboratories. Next. So any product, whether it can be a smart grid or smart grid related products or EV related products or any electronic products we design, it has to be undergone this particular test plan and it has to be executed by the proper method, and which the testing method which we that is electromagnetic interference compatibility comes under the characteristic tests, like as we discussed, radiated emission, conducted emissions, radiated immunity, conducted immunity, and surge levels, ESD levels, burst levels, voltage dips, magnetic fields. So these are all the particular things which has to be done to make the product compliance. Next. So these are all the typical test facilities are available in the electromagnetic laboratories. So based on the product size and your position of that is installation of your product, it can be, we can select the test facilities either any other shielded room or 30 meters shielded room, 3 meters shielded room. So various RS chambers. So various chambers are available, and particularly OATS, that is open air test sites, are available in the high hilly areas where there is no other external interference occurs, that is external radiation or any other disturbances occurs in that particular area. So devices can be tested using those areas. So these are all the typical EMC test facilities available in the laboratories. Next. So this slide shows this typical previous slide. This slide shows a typical anechoic chamber of 10 meter where the device or can be placed inside this chamber, and the radiated emission or conducted emission, whatever it may be, it can be measured in the outside the chamber. But the simulation of the signal, the emission and radiation can be induced inside the chamber, and the susceptibility can be checked with the help of how immune the system and how it reacts in the presence of electromagnetic interference noise. So that is the way that is the purpose of this particular test methods. Next. So you can say EUT is equipment under test is placed on the turnable bench or table, which is exposed, or which in the case of immunity test, it is exposed. In the case of susceptibility check, it is induced with the help of noise, with the help of antenna and other equipments available in the thing. And similarly, for ESD also, direct and indirect tests are available using other LISN or other various equipments are available, which can be used to measure particular the field of parameter we need. Next. So this is a typical EMS RS chamber, radiated susceptibility chamber. So here we can measure IEC 61004-2. You can see the antenna which is producing the noise, and we can measure the performance of the product in the presence of this particular noise level. As discussed, typical OATS, that is open area test sites, like for radiated emission site, this particular setup is made in the hilly areas, and it can be tested based on your product's implementation site, that is or installation area. And here it is specified the ANSI standards to be followed in the particular test sites. So there are various measurements also, measuring instruments also are available for measuring the test. There is EMI receivers, EMI spectrum analyzer network, vector network analyzer, and various measurement instruments are available for measuring particular thing, and we can correlate all those measurement results from the uh, uh, from the actual measurement from the thing, from the chamber actually, and those values can be benchmark against the particular standard which we are interested in things. So those particular instruments that is used, the instruments used in the particular EMC test laboratories are definitely to be followed under the basic guidelines or basic standards of this electromagnetic interference standards, which is set by the organizations. So not like every instruments we cannot use. So the guideline, basic guideline, the instruments has to be used for the particular EMC test laboratories. And the effects of the electromagnetic interference are we have seen in the smart grid applications, power converter, smart meter, and other communication technologies, and coexistence devices. So various malfunctions and other issues we have seen, and nowadays it is getting affected by actually it is getting affected by to the fields of organs of the human tissues, organ and tissues of the humans actually. So it affects the nervous system, visual system, immune system, and lot more system. So nowadays we need to improve our immune system. So every product, as an engineer, we electrical engineer or electronics engineer, we are we have to be very responsible enough to mitigate those particular electromagnetic interference noise, as nowadays we are dealing with very high speed signal operations in the case of data communication. So so importance of this electromagnetic issues is very thing. So with this note, I would like to conclude, and I am open for the discussion now. Thank you, everyone. So actually, my expertise is designing of high-speed PCB, and so my experience is actually is a high-speed PCB design area, and I am into this research side of electromagnetic interference, and um, so the simulation and the measurements of this electromagnetic interference I am interested in doing, and I am pursuing as a research thing. So if you have any anything you require, you can always contact me for EMI and C research related to the topics.
Participants, if you have any queries, please free to ask. Ma'am, some queries will be there in call message, ma'am.
Can you read out, sir? I cannot see those.
Exactly which standard used for smart grid?
I specified in the previous slides, no, sir. So there are for ESD we have some standard. Smart grid actually, it's actually a smart grid is not a single thing. So various standards has to be followed. For ESD testing level 61004-2 has to be followed, IEC. And similarly for conducted emission, if you are using the high speed data smart meter applications, the conductor emission for that particular standard number is there. So likewise, some 14 15 standards it has to be used based on the area. So that two slides represents, I have given the complete view of this standard numbers. Maybe you
Okay,
can
ma'am. Thank you.
slides to them. You
Ma'am,
can PPT.
another question will be there, ma'am.
Yes, sir.
Which standard you choose to use in your research?
Sir, actually, in my research, I have not chosen the standard number. Instead I use the frequency range actually. So several gigahertz to 20 gigahertz frequency of operations I have taken. For that particular frequency operation, I have designed a filter, and it proves that the filter operations, like it has the around 50 and 60 dB of noise level mitigation in the particular using because of this because of that filter. And that filter can be used where the application needs the particular for say for example 20 gigahertz application, it can be the filter can be applied. So that application product can be either it can be a smart grid or a EVs, other communication technology. So for testing the particular board, we can use the particular standard based on the product standards defined by the organization. So that is the flow I follow.
Thank you, ma'am. Ma'am, thank you for your presence.
Okay, sir. Thank you, sir. Thank you so much for inviting me for this to share my views on this particular topic. Thank you for the organizer.
Thank you, ma'am. We will meet in another occasion, ma'am. Okay, ma'am.
Thank you, sir.
Participants are requested to join another session, the second session by 11:30. So all are requested to cooperate with us to conduct this program smoothly. Next session starts by 11:30. Now I will share feedback link in call message or chat box. Please fill the feedback form. It is mandatory. So from that we could know the rating of each and every expert. So all are requested to fill the feedback link. So it will be posted in call message shortly. So feedback link is posted in call message. So go through that. Kindly fill the feedback form. So feedback form is mandatory. Without feedback form, we cannot come to know whether the expert what they provide the technical content is good enough or not. And also we will consider this feedback as a attendance purpose. So kindly ask to fill the feedback form. If anyone have a problem in receiving feedback form, please be intimated in call message. If there is any problem in opening feedback form, please be reply on in call message. Next session will start sharply by 11:30 a.m. All are requested to join 11:30 a.m. sharply. Thank you all. So I already posted a feedback link. And also participants are encouraged to ask queries at the end of each session. Presentation slides will be provided at the end of FTP.